So I am recording this for those people that are not on here, so they can watch it later. But no, we were waiting a couple minutes, and I had to step away for just a minute to do something real quick, so you did not miss anything, Melissa. No worries.
Thank you.
Assuming you were here just a second ago when I said that the nuclear lab data will be up today. That's the only thing that I have talked about. So yeah, that will be up this morning for you to look over. And actually, let me pull that up real quick just so I can make sure that what I'm remembering is what you actually need to do. Nuclear chemistry. So, I believe, yeah, so let me show you my screen here. So this is the nuclear chemistry lab report here, and I believe this is the correct version. We've had a few slightly different versions over the years, but I believe this is the correct one that I have on my computer. I do have a few quick things that I want to mention about the nuclear chemistry lab here. So number one, part A, I don't think I'm going to be able to do this part. I don't think I have the correct lead shielding to do this, and I'll double check when I go and actually get the data. But I will tell you specifically however I give the data to you, whether it's just in document form or whether I decide to make a video. I will tell you whether or not, but I don't believe that you will end up doing part A. I think that is going to end up being skipped, and that's just from a logistical standpoint, just because I don't think I have the lead that I would need to do this properly. Part B is going to be the main section that I will give you data for. So I will give you the data for relative thicknesses, and then the counts per minute, as well as percent transmittance. Or transmission, sorry, percent transmission. And so you'll make some graphs from that data. So just depending on how I decide to do it, I could send it to you with the data already in the data sheet, and then you would make the graph, or I could have a video where you would have to read the numbers off of the video. That's probably less likely, just because it would be kind of a pain to have to pause the video and read the dial and all of that, but I'll see how difficult that ends up being. But regardless, you would have to take that data, analyze it to make the graph for each of these different kinds of shielding materials. And those shielding materials will probably be things like aluminum or paper or things like that. Something that's fairly easy to get my hands on. And then part C, I know for sure I cannot do. There is a special kind of isotope generator that I have at my office that I do not have here, and I cannot go in and get it. So I cannot do part C, so do not worry about part C for this particular reaction. If I can find it, by the way, I might put up a video that I took like a year ago of what's it called? There's this, it's a cloud chamber. I forget the whole name, but essentially it's this special chamber where you can put a radioactive isotope into the chamber, and you can actually see the trails that are created by the ionized radiation as it's coming out of that radioactive sample. It's really cool, actually. And I took a video of that about a year ago, the last time I did this lab, which I guess wouldn't have been a year ago. It would be about 6 months ago. So if I can find that, I'll upload that as well so you can see that. But it's not going to be the same as the half-life part here. But I do expect you to be able to answer all of the questions in Part D. So all the questions down here in Part D you should be able to answer. So I think that is it. I think that's all I wanted to talk about in the nuclear chemistry lab. When you're using the Word graphing tools or printing it out and using graph by hand, either way is fine, as long as I can see what you did. So you could use the Word graphing tools, which I don't think I've even ever done that before. I don't like using Word to do that, but I know it's possible. You could print it out, graph it by hand, take pictures of it, send it in. That's also fine. Or if you prefer, you could copy and paste this into Excel and make your graph there. So as long as I can see the graph and the graph is clear, I don't care how you do it. Let's see. So the last question, yeah, let me double check just to be sure, but yeah, you can still do the last question. So it is referencing the same thing that was made in Part C, I guess, yeah. But you don't have to have the data from Part C to answer it. It's essentially just writing out a nuclear equation. Alright. Any other questions about the nuclear lab? Okay. So this week, the big thing is the exam. So this is the exam over thermochemistry, or thermodynamics, I should say, electrochemistry, and nuclear chemistry. So I would like to talk for a little bit about those. Let me see here. Oh, it's the wrong slides. Let me get the correct ones here. Let's see, we have 16. Yeah. 21 and
So will exam 3 be like the last one, same amount of time, same amount of questions?
yes. Yes, it should be very similar. I'm trying to remember how many questions were on the last exam.
Quite a bit. There were, I don't know, I think 25, 27. I don't know. I ran out of time. So,
Oh, okay.
but I think there was like 27.
Okay. Let me see. What was that? 27? Okay. I don't believe you, Stephanie. I knew I was boring you. I knew it. I'm just kidding. Hopefully you can find that soon. So let me see here. Okay, I already have it pulled up. So the if it was 27, it is shorter. I think the exam this time is 22 questions, if I remember correctly. It was 22. Um, and I actually was thinking yesterday, and I think I'll probably go ahead and do it. I was thinking that I would probably give you a little bit extra time on this exam.
That would be
So you have that extra time to complete the exam, extra 15 minutes, and I would like, unless someone has an objection, to spend a little time going over the big topics from the chapters and how I asked questions over some of these. This isn't quite as big of an issue with this class as it is in some of my other classes. The Gen Chem 1 class that I'm teaching right now, writing the exams for that thing was just the worst because we were doing Lewis structures and via CPR structures and things like that, where I really need to be able to see them drawing stuff, and I just can't. And so it was a pain to try to figure out a way to test Lewis structures where I can't actually see the students drawing a Lewis structure. So it's not quite that bad in this class, but I would still like to talk over some of the topics and how, just in a broad sense, how I asked some of the questions. So in chapter 16, I guess it was, the thermodynamics chapter, I do expect you to know generally here the differences between spontaneous processes and non-spontaneous processes. For example, is it possible for non-spontaneous processes to occur? Yes, it is. You just have to do something to get them to occur. They don't occur all on their own, but they can still occur. Spontaneous processes don't have to be fast. They can be very, very slow, but that still is occurring spontaneously. In addition to that, things that are spontaneous at one temperature are not spontaneous at other temperatures. So just understanding generally the idea of spontaneity in chemical reactions and how certain things are spontaneous and certain things aren't spontaneous, and just understanding generally that topic. There were some multiple choice or true-false questions that I put in there about spontaneous and non-spontaneous processes. Understanding entropy just generally as well. So entropy being the tendency to go towards disorder is how we described it, although we also talked about how that's not the best way to define entropy, but it essentially works for us, for our purposes. Let's see here. This is more just talking about entropy. Talking about how entropy increases with different modes of movement. So if I give you multiple different examples, like here's this molecule, which one would have greater entropy, you should be able to tell me that. And so we talk about that a good bit here. So again, the things that give it more entropy was larger molecules tend to have more entropy. Gases have more entropy than liquids, and liquids have more entropy than solids. So just understanding those basic trends of one thing having more entropy than another, and being able to identify those. You should be able to use this equation as well. Why is it not working? There we go. So this equation you should be able to use. So either solving for the entropy change of the surroundings or the enthalpy change of the system, either way you should be able to do that. And this is again just talking more about how entropy changes from one state to another, from one kind of solution to another. So just understanding generally how to do that. And then this is getting towards the Gibbs free energy equation, which is right here, which you should definitely know how to use. I guarantee you will have to use this equation on the exam. So either to find the Gibbs free energy or to find one of these or the other, you should be able to use this equation. As well as understanding that if that delta G value is negative, that means that you have a spontaneous process, and if it's positive, then you have a non-spontaneous process. And this is more just talking about using Gibbs free energy. Don't worry about the third law of thermodynamics. I'm not going to test you over the third law of thermodynamics. As far as standard entropies and calculating standard entropies using this equation, you should definitely know how to do that. As well as the same thing, but with Gibbs free energy, which is the next topic here. So you should, when you sit down to take the exam, you should either have your book with you or have access to the book on your computer or somewhere, so you can look up the thermodynamic data for entropy and Gibbs free energy. Because you will be doing one or both of these equations on the exam, where you have to look up the data for the products, look up the data for the reactants, multiply them by their coefficients, and then sum those together there. I heard a question come in. Let me check that. So in the OpenStax book, I want to say it's Appendix I. It's one of the appendices at the very back of the book. Let me pull that up. Go to here.
It's Appendix G.
Appendix G. Thank you, Melissa. So, no, that's not going to work. OpenStax, is that going to work? I know I have it on this computer somewhere, but I can never find it on here. But if you go to OpenStax, if you just Google OpenStax chemistry, it'll take you to the website. And so, if I look at the table of contents here, scroll down. Appendix G, Standard Thermodynamic Properties for Selected Substances. And so there's a whole bunch of different substances that it shows there. And so we would be interested in the second column and the third column when we were answering those questions. And I do want to stress here, be very meticulous in getting these numbers, because I'll tell you now, when I was making the questions, I really got frustrated with myself because multiple times I was trying to do it fast, and I would use the wrong data. So I would be doing a question for entropy, and I would accidentally use the Gibbs free energy values, and I'd be like, oh, dang it, go back and get all the numbers. I'd really get frustrated myself, as wasting time essentially using the wrong numbers. So be very careful that you're using the correct numbers, not just in terms of which molecule are you using, but you have 3 different numbers for every molecule, so be sure that you're using the correct number from the table. Okay, let's go back here. Alright, so like I said, be sure you know how to use these equations. You will be using one or both on the exam. You will not be doing this. So this stuff here, where you take different equations and you flip them around and multiply them by different values to get the correct equation, essentially the Gibbs free energy version of Hess's law, it's not going to be on there. So don't worry about that. But do know how to use this equation. So this is the equation for the non-standard Gibbs free energy. You will be using it on the exam. So know how to use this equation. And I will give you all the data you need to solve that. So be sure you know how to find Q, I will not make you calculate the standard Gibbs free energy. I think in some of the homework questions, they would give you the equation, and then you would have to go to the appendix to get the standard Gibbs free energy data for that. But I'm not going to have you do that, because that would essentially be two questions in one. Number one, can you go to the appendix and get all the correct data and tabulate all of it and add it up? The question that you'll have on the exam, I will give you the standard Gibbs free energy. And you will have to solve everything using the rest. So you'd have to use the non-standard state to work out what Q is, so that you can then solve the rest of it. Alright, same type of thing here with this equation. Be sure you know how to use this equation as well. So this is relating the equilibrium constant to the standard Gibbs free energy. And by the way, this is the same equation, it's just written differently. But either one will work. Just it'll depend on what I have you looking for. And I actually don't remember what I have you looking for in that. But you should be able to use this equation to solve for any part of the equation. Alright, I think that is it for this chapter. So in the electrochemistry, let's see here. So the beginning is mostly balancing, and there's a little bit here of just reminding you of how to calculate or determine redox numbers. I'm not going to have you calculating redox numbers. That was a Gen Chem 1 topic. This was just a refresher. So I'm not going to test you over using this table here. Although you should feel free to reference the table if you're working through the exam and you feel like you need to calculate oxidation numbers to help you solve something. But I'm not going to have you doing that in the exam, since, like I said, it is a Gen Chem 1 topic. I will have you balancing redox reactions, though. And I labored over this for a while as to exactly how I would have you solving and balancing redox reactions. Because there's not really a great way to do it. I don't really want to have you just typing in a balanced equation, because then we come across all kinds of formatting issues. And I couldn't really do it the way that I did balancing in my Gen Chem 1 class, because I did have to do that for an exam in my Gen Chem 1 class. Because in Gen Chem 1, it's just you have what you have at the beginning, and that's all, and so you could just give the students a spot to put in coefficients, and that's all you needed. But since with redox reactions, what you start with is actually not necessarily the only thing you have at the end. You can have, why isn't this working? You can have H plus, or you can have OH minus, or other things in the reaction at the end. I tried for a while to figure out some way of doing it differently, and I couldn't come up with a good way of doing it. So what I ended up doing was, and you will have to do balancing reactions, by the way, at least one. I can't remember if I have you do two or not, but there will be at least one redox reaction that you will have to balance. And so the way I ended up doing it was, I would give you something like this, except it was all on one line together. And you would have to fill in, and actually it wouldn't have the electrons in there. It would be like this. And you would have to fill in the values for the coefficients here. So the coefficients would not be shown like this. It would just be the molecules. And you will have to balance it on your own, and then fill in the correct values for the coefficients in the balanced chemical equation. the reason why I'm not super hot about doing it this way is because it actually gives you a huge hint as to whether or not you did the balancing properly to begin with. So this is actually a good thing for you in terms of getting the question correct, because I have to tell you, you have H plus on the left side of the reaction and you have waters on the right side of the reaction. And so if you are balancing the equation and you don't end up with that, then that's a big clue that you did something wrong. And so it's not my favorite way of asking the question because of that, but it does still give me the opportunity to gauge how well you are balancing equations. So that is okay. So that's how I've decided to do. Oops, wrong one. There it is. That's how I decided to do the redox equation balancing. And like I said, you will have to do at least one of these. I can't remember if I had you do 2 or not. I know I wrote more than 2, but not everyone gets the exact same one. But I think you only have to do 1, but I might be wrong about that. But you will do at least 1. That's just more of that. And also, the ones that you get could be in basic solution. So make sure that you're comfortable with solving for a basic solution as well, because that could possibly be what you get, or it might not. It just depends. Voltaic cells. You should be comfortable identifying all the different parts of a voltaic cell. So I could give you 2 different half reactions and say, if this reaction is spontaneous, what would be the anode, what would be the cathode, what ions are present, which direction are the electrons flowing, all that kind of stuff. You should be able to label all of those in an image like this. So you should be comfortable thinking about the construction, so to speak, of a voltaic cell and all its different parts. This is just more about voltaic cells. This is talking about the voltage of a cell. You should understand, generally speaking, why electrons move in an electrochemical cell. So they're moving from high potential energy to low potential energy, just like the water at the top of the waterfall falls down to the bottom. It's the same reason, going from high to low potential energy. It's just a different kind of potential energy. And so we go through a good bit of stuff here, just kind of setting up the idea of the half cells and using this table to find the voltage of different cells. And I guarantee you on the exam you will be using this table to determine voltages for different electrochemical cells. So you will be doing, let me see, where's that equation? There it is. So you will be using this to find the voltages of different cells. So it's cathode minus anode. Let me see what that question was. Should you print that table out? If you want to. If you have any kind of a setup where you could have it either on a separate screen or something like that where you could reference it, you can do that. Or you can print it out either way, just as long as you have access to it. And that should be in the in your book as well. Let me see. That particular image is from a different book. That particular table. I know OpenStax, go away. So this is what it looks like in your book. So this is the standard select standard reduction potentials at 25 degrees C. And so they have a whole bunch of different ones. Not quite as many as are on that table, but I think there's actually more in the appendix at the back as well. Let me see. Yeah, so Appendix L actually has a lot more. So if you're having trouble finding one there, Appendix L, which is, I don't know which page that would be in the actual book. but Appendix L, which is a few pages after Appendix G, would give you all of the half cells that you would possibly need, because this is more than even what's on that image on the other screen. So you should have all you need to solve those equations. $12.51. Thank you, Melissa. So be sure you know how to find the voltage of a cell using its two half cells. And also be able to identify whether it is going to be spontaneous using that voltage. So again, positive voltages are spontaneous, negative voltages are non-spontaneous for the cell. Alright, so this is... oh yes, so here we're going to get into relating the cell voltage to Gibbs free energy. You should be comfortable using this equation to either find Gibbs free energy or find the cell voltage. Be sure that you have this written down somewhere as well, Faraday's constant, because you will probably be needing that. And also, let me see here. Where is the normal? Yeah, so it's this. So this is the normal form of the Nernst equation, although it has volts. It's missing the unit volts there. But you should definitely know how to use the Nernst equation as well. So this allows us to calculate non-standard cell voltages. So again, here Q is products over reactants raised to their coefficients. So it's the equilibrium constant, just not necessarily the equilibrium. And N is the number of electrons that are being transferred. So if you have two different half reactions, one of them is transferring 4 electrons and the other half reaction is transferring 2 electrons, then N would be 4. Okay, any questions about those? Because that is pretty much it for this chapter. Because I'm not going to have you testing over the difference between a lithium-ion battery and a nickel metal hydride battery. Any questions? So will you be solving for something inside of Q? Essentially, is that what you're asking? No. If this was a paper exam, I might have you do that. So in some ways you guys have it a lot more difficult than some classes because you're having to do all this stuff online, but I'm doing my best to kind of try to even that out by not giving you quite as intense questions here. Because yeah, I mean, if this was a on-paper exam where I could see the work that you did, where I wouldn't have to worry quite as much about little math errors, because that's usually what gets people tripped up on those kind of questions, is they can get everything set up, but then all the algebra and everything gets messy. So I would and have in the past had people solve for, like you could ask a question, you know, if you have the concentration of these two things in the reaction, what concentration would you need for this third thing for the reaction to become spontaneous? So I could and have in the past asked questions like that, but I'm not going to do that on this one. So I will give you all the concentrations that you would need, and then it would be your job to solve for either. Well, it would probably be the non-standard cell voltage is what you'd be solving for, because the standard cell voltage you could just look that up on the table. You don't really need to use the Nernst equation to solve for that. Any other questions about electrochemistry? Okay. If you are in the process of typing, just keep going. Just type in your question. We'll get to it in a minute. But for now, the last chapter here, nuclear chemistry. The beginning here, we're just kind of introducing the idea of nuclear chemistry, refreshing you on stuff that you learned in Chem 1 about chemical symbols, mass numbers, atomic numbers, isotopes. All this stuff you should have covered in Gen Chem 1. And here again, we're just kind of introducing the idea of radioactivity. But now we're getting into the good stuff, the new stuff. Well, it's all good stuff, just new stuff here. So we have 5 different types of radioactive decay. You should be able to work out nuclear decay reactions for any of these 5 that could occur. The way that I ended up asking questions like this is I will give you either the parent, let's see here, either the parent nuclide, well that's a little bit too thick there. So either the parent nuclide and tell you how it is decaying, and then ask you to figure out the other daughter nuclide, or I could give you the daughter nuclide, tell you how the decay happened, then have you figure out what the starting thing was. So one or the other. So you're not going to be drawing out whole nuclear equations like this. Instead, what it's going to be, so if I were to ask this question on the exam, the way I would do it is I would say, you have uranium-238. It undergoes alpha decay. Other than the alpha particle, provide the following information for the other daughter nuclide. And then in the question, there would be a box with, next to it, it'll say chemical symbol. So it'll actually spell out chemical symbol, but then there'll be another box with mass number, and then there'll be another box with atomic number. And so your job is to work out what the daughter nuclide is. So in this case, it was thorium-234. And you would put into those boxes TH, 234, and 90. And so you are going to put in each of these parts into those individual boxes. This is the best way I could come up with to do something like this, just because I didn't want to have to worry about you getting the formatting incorrect. Because it is possible to put in formatting like this into Blackboard, but it's kind of a pain to find it. And so I can make sure you know all the correct parts this way, and it's easier for you to fill those in, I think. And so this is how those questions will be asked, where you have to put in each individual section, but you're not combining them together like it is shown here. So you should most definitely know how to do that and know how to do it for any of those 5 possibilities. You will not have to do all 5 of them, but you will have to do more than one. So I forget exactly how many I had you do. I think it's maybe 3. But I made a whole bunch. So I made like 10 or something, like 10 or 12 different ones. And you're going to do 3 or maybe 4, but I think 3 of those. So you won't have to do every single one, but you don't know which ones you're going to have to do yet, so you should know how to do all of them. And make sure you know how to do all of them beforehand. And actually, the gamma decay, if you remember, nothing actually changes with that one. And so in reality, there's actually only 4 options. There's only 4 different things where changes occur. So it's really only 4, since that 5th one is just kind of a, it's not nothing. It is giving off a whole lot of energy, but it's not actually changing mass numbers or atomic numbers. Alright. right. In addition to that, I do expect you to know the relative ionizing and penetrating power of the different kinds of radiation that are released by these processes. So just understanding that alpha particles, while they do have the highest ionizing power because they're so large, it's very easy to protect yourself from them. Gamma rays are the exact opposite. They don't have as much ionizing power, but it's very difficult to shield yourself from them. And then the beta and positron are in the middle. In addition to this, I do expect you to know that the strong force is what holds the nucleus together. So that is the glue between the neutrons and the protons that holds the nucleus together. I considered trying to insert images like this and ask you, what kind of decay is most likely to happen based on the location of this isotope, but I ended up not doing that. That being said, I did still ask questions where I give you an isotope, and based on the rules that we discuss here, mainly, excuse me, the rules mainly being the magic numbers, odd versus even numbers of protons and neutrons, and then the nothing with more than 83 protons being stable, those rules. Using those rules, you should be able to tell me whether an isotope is likely to be stable or not. And I made sure to only pick examples that were very clear. So you're not going to come across an example on the exam where you have maybe you have an even number of neutrons, but an odd number of protons, but you also have a magic number of this one thing. It's like, okay, so does the magic number outweigh having an odd number of this? Like there won't be confusion like that. So if you work out correctly how many protons there are, how many neutrons there are, it should be clear whether the isotope is likely to be stable or not. So be sure you know how to do that. And also, you should know just generally about different sources of background radiation. So you should know that radon is the biggest source of natural background radiation. And then depending on your personal situation, you might have more from medical x-rays or things like that. Let's see. You should know just generally that dosimeters are more passive ways of detecting radiation, while Geiger counters are actively measuring. I'm not going to have you writing an essay describing how they work, but just understanding that Geiger counters are actively measuring the amount of radiation, and dosimeters are measuring it as they go along, but they don't actively measure. It measures a cumulative effect of radiation. You should for sure know how to do kinetics with radioactive processes, and there'll be one of the questions on the practice exam is actually a kinetics with nuclear processes. So that will for sure be on the exam. So make sure you know how to use both this equation here, using the half-life to find K, or vice versa, and this equation. So this is the first order integrated rate law, because you will need to know how to use them. As far as nuclear transmutations, I'm not going to have you writing anything out in this, like in the shorthand way here or anything like that. I just expect you to know that nuclear transmutation is where you take one nucleus and turn it into another. That's all I really expect from you there. And then the rest of this stuff here, it really is just a very general knowledge is all I want you to have from here. Just understanding that radio tracers can be used to track things that normally can't be tracked, whether that be the movement of molecules in your body or the movement of molecules through a chemical process. Understanding generally what happens when you make a nucleus from individual particles. So we talked about that here, where the individual particles weigh more than the nucleus does. So if you take 2 protons and 2 neutrons separated, they have a certain mass, but when you put them together in a nucleus, they have less mass, and that is what we call the mass defect. It's because they're more stable. They're actually at a lower energy, and because they're at a lower energy, they have less mass, based on Einstein's equation. So just understanding that generally. Sometimes in classes in the past, I've actually had students calculating masses from energies. So like saying, we have a nuclear power plant and it produces this many gigawatts of energy, how much mass must have been lost to produce that much. Again, just because this semester is so weird, I'm not having you guys do that. It's a pretty fun calculation to do, though. It's actually kind of interesting. I do expect you also to know the difference between fission and fusion. Again, just in general terms. I'm not going to have you writing out equations or anything over this, but understanding that fission is taking a big thing and breaking it into smaller things, and fusion is taking small things and fusing them together into a larger thing. In addition to that, when it comes to fission, you should understand the chain reaction that we talked about in the video, and what critical mass is. So you should understand that critical mass is the point where we're losing as many neutrons as we're gaining. So we have essentially a stasis where we're not losing more than we're gaining, if you will. It's a different way of putting it. And so then supercritical masses are where we have the mass is large enough that we're losing fewer neutrons than we're producing in our process. And so that critical mass is where we have a self-sustaining fission process occurring. I'm not going to test you over the bomb or over nuclear reactors, although I would like to, but I'm not going to. And I believe that is pretty much it, because I'm also not going to test you over nuclear fusion. That was just kind of an interesting side topic. All right. Questions? Anyone have questions? Looks like we gained a few people as we went through, so that's good. Wow, someone was quick on the answering of that poll there. So at least one person is working on a question, I guess. So we'll wait a minute here. Will there be a lot of conversions using kinetics? What do you mean by conversions? Oh, no. No. I'm going to keep it as simple as possible. I'm not going to have you converting between energy values and masses. Like I said, if this was a normal class, I might put something like that in there, where you'd be converting between energy and mass. But no, there's not going to be conversions between megavolts and other types of power or other energy units or even mass units. It'll be very straightforward. No. So no conversion between megavolts and AMU. like I said, it's kind of a fun thing to do. At least I know I have kind of a warped sense of fun, but I think it's kind of fun to figure out, if I converted this much mass into energy, how much energy would I get? Because it seems like you're breaking the laws of science. Because up to this point, all your science teachers have told you, and I told you, if you were in my Chem 1 class, there's such a thing as the law of conservation of mass. You can't create or destroy mass. You can't create or destroy particles. And now we're saying, actually you can. See you, Stephanie. So yeah, it's with almost everything in science. There's an exception to almost everything in science. So if you had most of the stuff that your science teachers taught you as you were growing up, there's exceptions to practically everything. And I always kind of chuckle to myself when I go through Gen Chem 1, and I talk about there's so many things in Gen Chem 1 where I will tell students in class, this is true. Like, this is a scientific law. And then we get to Gen Chem 2, and it's like, actually, sometimes it's not quite that way. And it gives me, I internally chuckle in the middle of those classes. I try not to do it externally, because then the students are like, what are you laughing about? What's going on? And then I have to explain. They're like, what? All of this is a lie? No, it's not all a lie. It's just there are exceptions. Any other questions? Anything at all? Okay. If there's no other questions, then I think I will let you all go. Just to remind you, the exam is now available, as is the practice exam. They were available as soon as we jumped on the Blackboard site here. So please get those done. Get the practice exam done, not necessarily as soon as possible, but for sure a day or two before you expect to take the actual exam, so that you have some time to process the questions and get used to that before you take the real exam. That will be available until Saturday at midnight. Be sure that you start it well before then. You do not want to be trying to finish the exam at 11:50 at night on Saturday. So get that done as soon as possible, while still getting as prepared as possible, if that makes sense. Good luck. Talk to you all later.